Welcome to the 35th lecture of the MOOC on parallel algorithms. Today we shall see the first P-complete problem for NC reductions. This is the circuit value problem. So let us begin with the definition of the circuit value problem. The circuit value problem takes an instance of a circuit where each GI is an input or is Gj and Gk, the AND of two previous gates, or Gj or Gk, or negation of Gj for Jk less than I. So an ordered tuple of this form is called an instance of the circuit value problem. What is required in the problem is to evaluate the circuit. So we define the circuit value problem as the set of all ordered pairs G1 through Gn such that Gn evaluates to 1. We shall show that CVP is P-complete for NC reductions. From the definition of P-completeness for NC reductions, we know that a language is P-complete for NC reductions if it belongs to P, and then every language in P, NC reduces to this language. So for CVP to be P-complete for NC reductions, we must first show that CVP belongs to P. But this is easy to show. When we are given a circuit of this form, where each GI is either an input or an AND or negation of previous gates, then you can evaluate this circuit going left to right. Here G1 is necessarily an input, G2 is an input if it is not a negation of G1, unless G2 is the negation of G1. So these will form the basis, and then going from left to right, when we come to I, that is when we look at gate Gi, if Gi is Gj or Gk, or Gj or Gj and Gk, or negation of Gj, then Gj and Gk, where J and K are less than I, are already evaluated, because we are going from the left to the right. Therefore, Gi can be evaluated. The only other possibility is that Gi is an input itself, in which case Gi is readily available. So either way, when we move from the left to the right, the gates can be evaluated one at a time. So when we reach the right end, Gn would be evaluated. So all that is necessary is to evaluate Gn. Once Gn is evaluated, we know if the circuit belongs to CVT or not. If the circuit belongs to CVP, then the circuit evaluates to 1, otherwise the circuit evaluates to 0. So the evaluation of the circuit can be done in order of n time sequentially, which means there is a polynomial time algorithm for CVP. In other words, CVP belongs to P. So the first requirement is met. For CVP to be P-complete for NC reductions, it has to be in P first of all. That is satisfied. So now what remains to show is that for every language L belonging to P, L NC reduces to CVP. But then how do we show that? Let us say we take an arbitrary language L in P. So L is an arbitrary language in P. But then P is the class of all languages that are solvable in polynomial time using a deterministic Turing machine. Therefore, we can assume that L has a deterministic Turing machine. Without loss of generality, we can assume that this machine is a one-tip Turing machine, because always a multi-tip Turing machine can be simulated on a one-tip Turing machine. So, let us assume that L has a one tape Turing machine. So, let us say M is made up of these tuples. Q is a set of states, sigma is the alphabet, delta is the transition table, Q1 is the start state, and F is the set of final states. Let us say the set Q is made up of S states. The state space has a size of S, let us say, and let us say sigma is A1 through AM, this mode sigma is M. So, S and M are constants of the machine, and then let us say we are given an input W. We can construct a circuit from W in polylogarithmic time using polynomial number of processes, so that W will belong to L if and only if C belongs to CVP. So, what we are going to show is that given an arbitrary language L and an arbitrary input W to L, we can construct a circuit C from W in polylogarithmic time using a polynomial number of processors, so that W will belong to L if and only if C will belong to CVP. Therefore, if we have an algorithm for checking membership in CVP, then that algorithm can be used for checking membership in L of W. So, this is what we need to show to establish that CVP is P complete for NC reductions. So, how do we do this? So, we have the input W. Consider the execution of this machine on W. So, let us assume that W is given left justified on M's tape. So, W is the input to M, and that is given left justified in the tape. If this is the tape, then W is given at the left end. The rest of it is assumed to be blank. The rest of the tape is assumed to be blank. So, the input is given at the left end of the tape, and we assume that the machine starts at the leftmost cell. So, M starts in state Q1 with the head on cell 1. We assume that the cells are numbered consecutively from the left end. So, the leftmost cell is numbered 1. Now, we are going to construct a circuit C. To construct C, we will establish a number of signal points. These signal points are denoted like this. We have signal points of the form HIT, we have signal points of the form CIJT, and we have signal points of the form SKT. Here I varies from 1 to T of n, T varies from 0 to T of n, and K varies from 1 to S. So, you can see that there are order of T squared such signal points, T squared of n signal points, where T of n is the time bound of the machine. That is, when M is given an input of length n, we have a guarantee that M will come to a halt in T of n steps. And we also know that T of n is a polynomial in n. That is because M is a polynomial time bounded machine. So, we have established order of T squared of n, which is also a polynomial in n signal points. So, let us see what these signal points mean. H of IT is going to be 1 if and only if the head of the machine is on cell I at the tth time instant. H of IT is going to be 1 if and only if the head of the machine is going to be on cell I at the tth time instant. Similarly, Cij is going to be 1 if and only if cell I contains symbol aj at the tth time instant. So, now you can imagine what SKT is going to be. This is going to be 1 if and only if the state of the machine is Qk at time t. So, we have order of t squared of n signal points of the sort, and we are going to connect these signal points using gates to obtain a circuit. To obtain the circuit, at the lowest level we have Hi zeros, C ij zeros and Sk zeros. So, these are the signal points corresponding to time 0, and then at the next level we have Hi ones, Cij ones and Sk ones, and going all the way we come to Hitn. The algorithm is going to halt within t of n steps. So, we do not have to consider time that is beyond t of n. So, we have now established signal points of the sort. Now, all that is necessary is to connect up these signal points using logic gates, and then we will have the entire circuit laid out. And now, what is the circuit that we want? We want a circuit which will evaluate to 1 if and only if the string is accepted by the language. Now, let us assume a convention that when the Turing machine halts, if it is going to accept the input, it will write 1 in the first cell. If it is going to reject the string, it is going to write a 0 in the first cell. So, all we have to do is to check whether the cell, the leftmost cell is going to contain a 1 at the time the algorithm halts, which is at time t of n, cell 1 should contain a 1. This is precisely the case where C1, which is cell 1, contains A1. So, A1 will be denoted using 1 again, t of n happens to be 1. This is if and only if W belongs to L. So, if you manage to connect up the signal points in such a way that the signals all will satisfy the intended meaning, then we only have to check whether C11 t of n is 1. Okay, now let us see how the circuit can be laid out. So, first of all we have to define the inputs to the circuit. So, Hi 0 is 1 if I equal to 1, 0 otherwise. What it means is that at time 0, that is when the machine starts up, the head is at the leftmost cell, which the leftmost cell is numbered 1. Therefore, H of I 0 is 1 if I equal to 1 and 0 otherwise. So, it says that H of 1 0 is true and H of I 0 is false for every I other than 1. In other words, the head is on cell 1. So, if we set Hi 0 to 1, if and only if I equal to 1, then we have the intended purpose. The H 0 values are all appropriately set. Then let us consider C ij zeros. That is, we want to assert that at the beginning of the machine, cell I contains symbol aj. But then at the beginning of the machine, which cell contains what is decided by the input. Therefore, cell I will contain aj precisely if the ith symbol of the input happens to be aj. So, this is if and only if the ith cell contains aj. This will be 0 otherwise. So, you remember that here I varies from 1 to t of n. That is because a Turing machine which is t of n time bounded cannot use any more space than t of n. The machine in the worst case will be using one new cell in every single step. Therefore, if the machine halts in t of n steps, it will use at most t of n cells, and we are accounting for all these t of n cells. Initially, the input is written left justified on the tape. The input has a length of n. If n happens to be less than t of n, then there will be some extra space that is used by the machine. So, initially the machine will mark out these extra space with blank symbols, and the input will be kept in the first n symbols. So, we have initialized Cij values for such T of n I values. So, Cij values are also appropriately set for time 0, and then Sk0 will be 1 if and only if k equal to 1. That is, the state is supposed to be q1 when the machine starts up, it is 0 otherwise. So, these settings will form the basis, and the settings are all appropriate. The Hi values, Cij values and Sk values at time 0 all represent the position of the head, the contents of the cell and the state at the beginning of the execution. So, this will form the basis. Now, let us see how H I t plus 1, C I j t plus 1 and S k t plus 1 can be obtained from the H values at time t, the C values at time t and the S values at time t. So, using these values we will be able to establish the t plus 1 values for H, C and S. So, first let us consider H I t plus 1. For this, let me define I r as this set. I r is defined as all ordered pairs k j, so that delta of q k a j is a tuple of this form. Here the star denotes a wildcard, it does not matter what it is. So, I r is defined to be the set of all ordered pairs k j, so that when the state of the machine is q k and the symbol scanned is a j, the machine has a transition of this sort. It will, we do not care which state it enters and what is the new symbol that it is written, but we insist that the head should be moving right. So, these are essentially all k j ordered pairs which will cause the machine to have a right movement. So, these are the k j pairs or state symbol pairs that cause the machine to move right. There is a read right head to move right. So, the machine has a rightward movement when one such an ordered pair happens. Similarly, let us define I L as the set of all k j pairs that cause left movements. So, here delta of q k a j must be a tuple of this form. So, with these definitions, we can now define H of I t plus 1. That is, we want to assert that at time t plus 1, the head of the read write head, the read write head is going to be on cell I. Now, this is possible if either in the previous time instant the head was at position I minus 1 and the machine had a rightward movement. So, let us see what it says. This term asserts that at time t the head was on the I minus first cell. Not only that, for some k j belonging to I r, that is for some state symbol pair which causes the machine to move right, the I minus first cell contained a j in the previous time instant, and also the state of the machine was q k in the previous time instant. So, in the previous time instant we had the composition of q k and a j, the state was q k and the cell scanned contained a j. Now, this pair is a right movement inducing pair, therefore, the machine would have moved right. So, what we are asserting is that in the previous instant the head was on the I minus first cell and that I minus first cell contained some a j and the state happened to be some q k, and this q k and a j were so that they would have induced a right movement in the machine. So, the machine would have moved to the next cell, which is the ith cell. That is how the head came to be in cell I in the t plus first step. Now, this is one possibility, that is the head could have come to the ith cell through a right movement, but then the head could have come to the ith cell through a left movement as well. So, that is the other possibility. So, either this could have happened or it could be that in the previous instant the head was on the I plus first cell and there existed some left movement causing k j pair. So, that this was the k j pair that was prevalent in the tth time instant. If either of this happens, then the head would end up being in the ith position in step number t. Now, if you have these signal points, we know hi minus 1t, hi plus 1t, and let us say we know ci minus 1 jt, skt, ci minus 1 jt and skt. We have all these signal points for every kj belonging to IR and for every kj belonging to IL. Then we can construct a Boolean circuit for HIT plus 1 using AND, OR and NOT gates. In fact, we do not need a NOT gate here, we need only AND and OR gates. But then such a circuit can be obtained in order of 1 time using T squared of n processors. So, what we say is that from the signal points at level t, so these signal points involve the H signals, C signals and the S signals. From all of these, we can obtain the H signal points by appropriately setting up circuits from the tth level to the t plus first level. Each box will contain a set of AND OR gates and the depth of the circuit is going to be order 1. As you can see, this circuit, this Boolean expression has only a constant depth. It is a disjunction where each disjunct is where each term is a conjunct and so on. So, there is a constant depth to this Boolean circuit. So, the Boolean circuit can be established in order 1 time using T squared of n processes. That is, setting up of this circuit will require only order of 1 time using T squared of n processes. So, we know that all the H signals at level t plus 1 can be connected up to the signal points at the previous level using Boolean circuits in order 1 time. T squared of n is a polynomial because T of n is a polynomial. So, we know that this can be established in NC. Now, let us come to the Ci j t plus 1 signals. Ci j t plus 1 wants to assert that cell I contains symbol j at time t plus 1. Now, this is possible if the cell that the machine scanned in the previous step, that is in the tth step, was not I and cell I contained symbol j. What it means is the head was elsewhere. The head was not in the vicinity, the head was not on cell I. If the head was not on cell I, the machine would not have been able to change the content of cell I in step t. And if cell I contained Aj in step t and the head was elsewhere, then the content of cell I would continue to be symbol Aj in the t plus first step as well. So, this is one possibility. This is one way how cell I could contain symbol Aj in the t plus first step. Another way is for the machine to actually change the cell to get Aj in cell I in step t plus 1. That is possible only if the head was on the ith cell in the previous step and we take a disjunction over all ordered pairs Kj prime of Ci j prime t and Sk t. Thus, we want to say that there exists an ordered pair Kj prime, so that Qk Aj prime is an Aj writing move. That is, if the previous state happened to be Qk and the scanned cell contained Aj, in that case then the machine would have written Aj in the cell scanned. So, such a Qk Aj prime was in contention in the previous step. In that case, if the cell scanned was I and the cell contained Aj prime and the state was Qk in the previous step, that is time t, then the machine would have rewritten the content of cell I to Aj, because that was a Aj writing step. So, this is how we can synthesize Cij t plus 1. So, you can see that it uses only H, C and S signals of time t. It uses negation and an OR, and the depth of this Boolean expression is only a constant. Therefore, we see that Cij t plus 1 can also be, that is, circuits computing Cij t plus 1 from H, C and S values at t can be established in order 1 time using T squared Fn processes on any PRAM. Now, finally, we come to signals of the form Sk t plus 1. For this, we need to define a set Ik. Ik is defined as the set of all ordered pairs k prime j, so that delta of qk prime aj happens to be qk with wildcards. So, Ik is the set of all state symbol pairs qk prime aj, so that when such an ordered pair happens, the machine switches into state qk. So, these are ordered pairs which induce state qk. Now, with Ik, we can write the expression for Sk t plus 1. We want to say that the machine is in state qk at time t plus 1. This is possible if so what does it say? The rex is an I ranging from 1 to t of n, that is, the rex is some cell on the tape. The tape is going to use t of n cells. So, there is some cell on the tape, so that there is a qk switch inducing pair k prime j, so that the state was qk prime in the previous step, the head was on the ith cell, so the head was on some cell, and this cell contained aj, where aj is the other half in this qk inducing pair. If that is the case, then the state of the machine should be qk in step t plus 1, as indeed would be the case. If there is some cell I which contained aj in the previous step, and in the previous step the state had been k prime, and this k prime aj k prime j pair happens to be a qk state inducing pair, in that case then in step t plus 1 the state has to be qk. Now, this is a much larger Boolean expression than the previous one, because there are many more disjunctions here. But still, using a sequence of AND OR gates of length t of n, Sk t plus 1 can be obtained from H, C and S signals at level t. And such a sequence can be generated in order of log of Tn, which is order of log n time, using T of n processes, using T squared of n processes. What it means is that the entire circuit, the circuit with gates between the levels, so we have T of n such levels. For times varying from 0 to t of n, there are t of n plus 1 such levels. These levels can be interconnected with a separate set of processors for each adjacent pairs of levels in polylog time using a polynomial number of processors. So, the circuit itself can be drawn up, the circuit can be written out. Visualizing the circuit and writing it out in this form are essentially the same as you can figure out in NC, that is in polylogarithmic time using a polynomial number of processors, which means when we are given an input W, which is a potential input for the language L, using the transition table of the Turing machine for this language L, we can write out a circuit, so that this circuit will evaluate 1, that is, there is one signal point in this circuit which will evaluate 1 if and only if W belongs to L. Which is that signal point? It is C11 T of n. That is, when the machine comes to a halt at the T of n step, the first cell should contain A1. A1, let us assume, is symbol 1. So, in that case W should belong to L, and only in that case will W belong to L. So, evaluating this circuit can essentially check the membership of L. So, this establishes that CVP is P complete for NC reductions. That is, we have just now shown that any arbitrary language L in P is NC reducible to CVP. CVP is at least as hard as all these languages. In addition, CVP also belongs to P. So, CVP is P complete for NC reductions. So, there is indeed a language which is P complete for NC reductions. But then what it means is that if CVP has an NC algorithm, then every language in P has an NC algorithm. How do we show this? Suppose this is the hypothesized NC algo for CVP. Of course, no such algorithm is known. Suppose this runs in order of log n power k1 time using n power k2 processes. And then let us consider an L to CVP translator, which we have seen just now. This will take an input, a potential input to L, and will produce a circuit. Suppose this translator, since this is an NC translator, this should run in log n power k2 time or log n power L1 time using n power L2 processors. Then by the juxtaposition of these two algorithms, we will have an NC algorithm. When we juxtapose them, we have to use Brent's scheduling principle. Each of these individual components of the algorithm are polylogarithmic time algorithms, and each has a polynomial cost. So, the total cost is a polynomial as well, and then the larger of these two time bounds can be used for finding the number of processes that should be used in Brent's scheduling principle. Such an execution of this juxtaposition will be an NC execution. Therefore, we have established that if CVP has an NC algorithm, then every language in P has an NC algorithm. And this is assumed to be unlikely today, because even after several investigations, we still have not been able to find a P algorithm for any of find an NC algorithm for any of the P complete languages for NC reductions. And nor have we been able to show that NC is not equal to P. So, this question remains an open one, exactly the same way as this question remained. We do not know whether P equal to NP. Similarly, we do not know whether NC equal to P. In the next class, we shall see some reductions from some commonly encountered problems like depth first search, etc., to the circuit value problem, and that will establish that some of the very common, very easy to solve sequentially problems are hard for parallelization. For example, depth first search has a very easy sequential algorithm, but it does not have an efficient parallel algorithm as of now, and it is rather unlikely to have an efficient parallel algorithm, since we do not know whether NC equal to P. If NC is not equal to P, then DFS will not have a polylogarithmic time polynomial processes solution. So, this we shall see in the next class. So, that is it from this lecture. Hope to see you in the next. Thank you.